This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SE-radio.
Hello everyone, this is Felienne for SE Radio. Today here with me I have Riccardo Terrell. He is a software engineer and a Microsoft MVP who is passionate about functional programming. He is active in the F# community and he started the Washington DC F# user group. He's also the author of the Manning book Concurrency in .NET, Modern Patterns of Concurrent and Parallel Programming. He believes in polyglot programming as mechanism for finding the right tool for the job. Welcome to the show, Ricky.
Hi, Felienne. Thank you for having me. I'm very excited to be here.
Thanks. So the topic of today's show is concurrency, because that's also what your book is about and what you are an expert on. First things first, what is concurrency?
All right. Well, concurrency, you can think about concurrency as a real programming model where there are more than one computation that is executed in overlapping time, like interleaving fashion. And really simply, you can think as a concurrency, the capability where several tasks can run at the same time. But what I really like to think about concurrency is a step forward, is really a way where you can structure your programming solution to solve a problem that may or may not be parallelized. And we talk about parallelism probably coming later. But really a way to structure your program. And then concurrency, parallelism will become like a side effect when all these parts can run, in independent tasks.
So simply said, stuff is happening at the same time. Is that correct?
That's correct, yes.
Are problems inherently concurrent or are solutions concurrent?
Well, really the main idea is how you can break the program in a smaller independent unit of work, right? So really, every problem become inherently concurrent, as you said. And parallelism, which aim to leverage the resources of the machine context and improve the performance, become like a positive side effect, right? Because now we can have a program that run and leverage multi-core. So really, it can apply to this solution and benefit from concurrency because we can design the code that is able also to self-adapt on the resource available on the machine, right? So for example, you can write a program, in a concurrent structured manner so it can run in a single core. However, when you run the same code in a multi-core machine like 4, 8, 16, well, automatically, the program runs faster because able to self-adapt and increase the speed automatically because leverage all the resources.
Okay. And this is a little bit confusing to me because there's so many words and lingo around concurrency. And when I read your book, you also mentioned different words like concurrency, but also multithreading, multitasking, parallelism. Can you help the audience figure out which is which? So let's start with the first one.
Sure.
What is multithreading? Well,
so multithread really is it's still part of the family of concurrency, right? Is a form of concurrency, but multithread is based like on the same process when multiple threads are running on the same process. So pretty much all the programs are concurrent, right? But then we can have, as you said, different kind of behavior. And like for instance, parallel programming is also concurrent, but doesn't mean that concurrent is also parallel. So, for example, parallelism is really based on is constrained by the hardware. Okay, think about concurrent can be a program that runs in a single core, and through context switching, the program, the scheduler, run different part of the program. However, in parallel programming, you can achieve parallelism only through multi-core machines. So really, parallelism is concurrency in a multi-core machine, pretty much. So parallelism is hardware constrained. Multitasking is still like concurrently, but different from multithreading is the fact that you can have multiple threads that run on different processes, right? So it doesn't really mean, that these are multitasking or run in parallel, but they give you the effect, the illusion they run in parallel because, again, the scheduler can switch the thread or execution between these tasks.
Okay, so the three of them, multi-threading, multitasking, and parallelism, all are different forms of concurrency.
Yeah, that's correct, right? And the only thing is parallelism is concurrent, but is hardware constrained.
Hardware constraint. Yeah, got it.
So really, exactly different operation at the same time. Instead, concurrency more like give you the illusion.
Can you give us some examples of typical programs that you could address with or that you should address with concurrent solutions?
Sure. So, really, any sort of application that can benefit from partitioning and running parallel, different tasks in a multi-core machine. For example, a video game, financial, stock trading, image processing, machine learning also is very much, can be leveraged from parallelism. Like I did a little work project, in a neural network, and where really can leverage quite well parallelism when all the cell the network can be computed at the same time. And so these days, for instance, one that is very trendy is like think about self-driving car that to make a decision very quickly. This can be all computed in parallel to maximize the performance, the speed, because it's like life-saving kind of decision, right? So really, any sort of modern software really today's require high performance computation, right? So including the capability to produce a great user experience from the UI back to the back end part of the application when the computation actually happen. So, and then also any sort of algorithm that can be easily parallelized. There's actually a branch of algorithm called inversely parallelizable, which means that it just requires a little effort to be breaking apart and running parallel. Like, for example, I can feel like the Monte Carlo simulation or any sort of fractal computation. So, so a lot of stuff can be leveraged can leverage concurrency.
And in summary, what I think you're saying is parallelism is concurrency is a good solution when you have a problem and you need speed, and it's easy to break it into separate parts that can be calculated independently from each other.
That's
right?
correct. Yes, that's correct.
Got it. So the next question is, why is concurrency hard? Why are we devoting an episode to this? Can you name some of the things that make concurrency interesting and hard?
Sure. Well, the main problem is that still today mainstream languages were not designed with concurrency in mind, and the problem that back in the day there was not the need to think about having multiple thread running multiple cores. So these days, although we are facing this new challenge where we have machines that have multiple cores to be computed, in parallel, and but these mainstream languages, they're still based on mutational state, and that's the main problem when we have mutable state that can be shared. So at this point, we have multiple threads that can access the same memory slot, and it can be lead to unwanted behavior such as race condition, right? Think about two threads read the same variable but at the same value, but then thread one write the variable and update the variable, and then thread two have a value of the variable that is not the latest one. So you can run an unwanted behavior, and even the program can even crash if extreme cases. So to overcome this limitation, this problem, they've been introduced primitives such as locks, mutex, semaphore in these languages, but as the name implies, lock, it really prevents the program to run in parallel. What it really does, it protects this memory slot to be corrupted, to have like a race condition. So you like miss the point of parallelize your code and leverage all the resources. So, and also this lock is very complex to use because you might protect this memory slot from the access of multiple threads, but then when they have a program more complex, you can run in another sort of a bad situation, such as deadlock, when two threads are waiting each other to release a lock to continue the work. So they're waiting each other, and the program stop the computation, indefinitely. And this is a problem that is very hard to debug, right? Both race condition, deadlock, because very hard to debug, especially because when you push the code in production, you can imagine that the environment that you run in your local machine, when you program your code initially, run differently than in production. That probably is more they have to, let's say, respond to a higher rate of request, so is under heavily stress, right? So it might work in your machine, but in production, this problem that then is also very hard to reproduce on your local machine and debug. So there's a different kind of problem. It also depends on where the machine is running, right? For instance, I have a case that happened a little while ago that was very hard to investigate, where the program was run in a machine that actually was using preemptive scheduler, which means that was preemptive when you have a scheduler that run a task, and the task is run the computation until the end. And but then was passed to a machine that was using a cooperative scheduler, which means use a context switch in the back to make the system more responsive. But for this kind of behavior, really, there was some bug introduced in the system that was not detected in the beginning. So it's it's a very complex, kind of programming model, concurrency in general, and very hard to debug.
So, in summary, what you said is one of the reasons that concurrency is so hard is because programming languages weren't really designed for concurrency from the beginning. So, you run into issues when you want to implement concurrency in languages that weren't really designed for it. Is that correct?
That's correct. Yes, that's correct. So, yeah, the main problem really the share of state, the introduction then of primitive like locks that can overcome this kind of issues, but then you introduce extra complexity such as extra overhead because you prevent actually the program to run in parallel, and then it's very hard to debug because as I mentioned, sometimes in your local machine works correctly, but in different kind of environment with different kind of scheduler, different kind of heavy stress work to complete, this is very hard to detect, right? And as I said, that when you run this kind of problem in production, it's very hard to reproduce, especially this idea of that the bug can disappear when you also attempt to debug it, right? So the Heisenberg idea. So I think that we see this day that system also so they try to step back from this kind of concurrent programming because they have too much complexity, and they try to simplify the programming model for a developer that can focus most on the logic rather than on the complexity of concurrent programming. For instance, one that is very well known like is Node.js, which actually is provide a very high throughput, but it's really based on a single threaded in an event loop, single threaded. But what it does is that it processes all the incoming requests in a I/O manner, which is input output, which is a no CPU bound operation. So it's asynchronous. So it's able to spawn and compute many operations in a synchronous manner, leveraging something that is really keep the CPU light, and because it's single threaded, it really remove all the hazard that are consequences from concurrent programming, such as I mentioned, deadlock, race condition, and to actually have to be able to run and in parallel, you actually spawn different kind of different Node.js processes, right? So it's really like become too much complex. So redesign, the architect the application to be simpler.
So what you're saying is, rather than doing concurrency in a programming language that wasn't designed for it, it would be a better approach if programming language designers would solve the concurrency issues in the programming language itself, so that it wouldn't be a problem for the programmers. Is that what you're saying?
That's correct, yes. And we see these days that more and more modern programming languages are, embracing this kind of programming model. So we have like Go, for instance, or Rust. They are start to introduce immutable structure construct in a language. So it become immutable as default, like F#, Scala, and so forth. They allow you to write mutable code, but you have to be explicit. So really almost the opposite that of mainstream programming language like C++, Java, and C#, right?
Let's take a step back here, because you mentioned a bunch of interesting things. Most specifically, you said some languages have immutability as a default, but not everyone might be familiar with what you mean by that. So could you explain that? What is immutability, and what does it have to do with concurrency?
Yeah, sure. Well, so immutability is the idea that whenever you assign a value, bind a value, this value will never change. And as you can imagine, as I mentioned, one of the problems with concurrent programming is the share or mutable state. But now, if you share a state that cannot change, well, it becomes thread safe intrinsically, right? Because now, because the value never change, multiple threads can access it and without any problem. And even from a mindset of the programmer, it can be challenging if you come from an experience where you wrote imperative programming for many years, which is based on mutational state. But it requires a little bit of mindset in the beginning and big investment, and some have bad headaches for sure, but it's going to be paid off over time. In fact, as I said, even programming languages like Java and C#, they were not designed with the mutable structure. Now they're more and more introducing this concept in the language because they realize that the best way to solve this kind of problem is from the root, right? Removing completely what could be the source of the problem, which is a mutable state.
Yeah, so you mentioned something there about shared state being the problem in concurrency. Could you give an example of a problem where shared state is the issue in a concurrent solution?
Sure. Well, so any time that multiple thread can modify a value that is shared, right? So, for instance, a very bad design, called share global state. But this is a classic example where if you have like a global counter and it's not protected, and you have multiple requests coming in a server and update the counter at the same time, well, it can happen that the counter won't reflect the real number, because the real value, because one thread can access and grab the value, and a second thread coming in change the value. So now the second thread update the value that was already be changed and even a race condition, right? So this is like one of the classic problem of a race condition.
But how do we solve that with an immutable data structure? Because how would the alternative solution look like? Because you have some shared value that the both threads need to write to.
Yes.
The both of them have an immutable data structure. How are we going to consolidate the result of, let's say, a MapReduce algorithm?
Right. Well, so that's a good question. Like as I said, it really become like a little bit a different mindset. A change of mindset is a different paradigm. So it become like there are different kind of approaches. One is definitely try to figure out a way to redesign the program to avoid the change of state, or to avoid the change of state and leverage immutability. One of the solutions that or technique used, for instance, in a mutable structure are called compare and swap, which is used especially when design concurrent algorithm to achieve synchronization without the engagement or deployment of locks, right? And compare and swap is in a low-level instruction that work atomically and compare really the content or the value of a memory slot with in a given value, and if both have the same, they modify the content and memory location with a new value, And this is, as I said, is done in a single atomic operation, and is guaranteed that each thread are able to access to the latest and true value. For example, in .NET, there was introduced a little while ago immutable collection, which is a bit different from concurrent collection. Immutable collection really the idea that whenever you create this collection, they will never change. So if you add or remove an item, a new collection is created. And to modify actually this collection, there is a library that use underlying technique that I mentioned, the compare and swap. What's interesting though is that whenever you use a immutable structure or immutable collection, it uses something called structural sharing property, which is very cool because now instead to create a copy every time that you add or remove an item or you change an item, actually really leveraging immutability, and instead to create a new collection, just create a point and reference the previous collection with the updated value. So at this point, really immutability, it completely embraces not just to remove the thread hazard, but also to reduce, memory consumption and memory pressure and so forth. So I think it's pretty cool.
So slowly we're moving into talking about data structure, and you've just mentioned the immutable collection. Are there other examples of concurrent data structures or structures that are really useful if you're doing concurrent programming?
Yeah, so like for instance, so there are two different kind of collection, like the concurrent collection and immutable collection. The concurrent collection are really designed to share state among thread, but the challenge it become when you build a structure that can create more complexity because you want to really create this collection that very performant. So it's very hard to have both benefit to be able to share state among thread and also be able to have high performance. On the other side, as I said, immutable collection, well, because the collection cannot change, so they are safe to be shared among thread without penalty in performance. One of the most used concurrent collection is the queue, right? Because used when actually queued up work to be computed later when the resources are available. For instance, one classic, and simple pattern, the producer-consumer pattern. So you have a producer that queued up using a concurrent queue and some items, and the other side, the producer in a different process or different thread, is going to pick up from this queue the item in a thread safe manner.
So is this the same as a thread safe data structure, or is a concurrent data structure different from a thread safe data structure?
No, they're very similar, and it's a very subtle difference. The main difference is the underlying implementation, where thread safe is being implemented just to guarantee that there won't be any sort of data corruption. Rather, the other side, the concurrent structure, has been implemented with more sophisticated algorithm to guarantee also performance. Like for instance, concurrent structure can have implemented a compare swap algorithm or they fall back to a lock kind of approach if they're not be able to compare swap the value, the underlying value when you mutate the collection. So they're just very complex collection that guarantee also the performance.
Okay, thanks.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
Let's talk about debugging, because debugging is going to be very hard in concurrent programming, right?
Yeah.
In the beginning of the episode, you already briefly meant the famous Heisenberg bug. This is a bug that you cannot easily reproduce, and if you try, the bug will change. So can you talk us through your typical workflow when debugging a concurrent program? Maybe you have an example a recent example that you ran into where you had to debug a concurrent issue? What was your approach?
Yeah. So first of all, yes, you're right. Concurrent program is very tough to debug, and there are many different kind of component and wheel the spin. So there is a lot of friction to take care. Recently, I work in this rule engine application that initially was designed to run multiple validation for a set of records, but the idea that would just spawn in many tasks, like for one task for each record to validate. And you can imagine there was like thousand and thousand record. So the application was actually running slower than a sequential version application. And the problem is that there was a lot of extra overhead introduced in application with extra context switching, and really the scheduler were going crazy to figure out which task run is switching to the other and so forth. So one of the technique that can be used, first of all, is abstract away the program to redesign it more on a granular level. So I think that one some application to be redesigned to run in parallel before to try to optimize the low level algorithm should be like think more high level. And like for instance, the distribution of the work, instead to have like a multiple task run for each record in the case of the rule engine, and can be done more high level when you have like a producer consumer part that was mentioned earlier, or this kind of redesign. This pattern that can be help you to redesign the application at more high level. And then when you implement this pattern, you figure out where are the bottleneck of the application, and then continue to redesign and leveraging parallelism to improve the performance. And then you start to narrow down until you found the low level of more small algorithm that can be optimized. So in this specific case, I breaking apart the pipeline each rule engine instead to run all in a single thread. It was each engine was running separately. So I'm really using like a pipeline pattern where each step of the pipeline was able to consume the resources and load balance the work with the other step of the pipeline. And to debug this kind of application, the complexity became when you have multiple threads running parallel, because now whenever you set a breakpoint, well, you just stop or block in the breakpoint the current execution thread, which means that you can stop there, but at the same time in the background, the other executing thread are still running. So if you try to step forward to the next step with the debugger, most likely you won't hit the next line of the code that you are currently, but you want to run in a different part of the application where the other thread is running, and you start control all the application, and it start to be very complex. So in this case, one approach, a simple one, is really control the scheduler and be able to set in the configuration level the level of parallelism. So in this case, you can just set a single threaded. So you defeat the parallelism, but you still be able to flow to the pipeline step by step. And then there are tools out there that can help you definitely to debug and the multi-thread application. One that I really like is a concurrent visualizer. They actually is able to run the application and provide you like really a multi-thread map and see how the application perform.
So is this like a visualization? You visualize
That's correct.
How the threads interact with each other.
That's correct. And this is very useful because there are different kind of cases where just by the graph, like a visual graph, you can detect if you have run in some sort of bad scenario, such as I was saying earlier, we have many tasks running more than should be. You have something called oversubscription, which is a pattern that you recognize when you see the scheduler start to context switch multiple tasks, and that's when the performance will be penalized by the extra overhead. Another, pattern that you recognize through a graph is the lock convoys, when the lock that protect, the memory slot, it contain or restrain the thread for longer time than the other thread are coming, and they're waiting for the lock to be released. So this really become, it's like the convoy log. So you have multiple tasks queued up waiting the release that is lower from they arrive.
And it visualizes that too. It visualizes tasks that are waiting for a certain memory element.
That's correct. Yes, and it's a great tool. And of course, you can other be like called old school kind of approaches, such as you can have very sophisticated logging trace where actually you can log and detect the stack of the thread and the thread ID. You can create a snapshot of the state of all the current thread that are running the process, so you can analyze that state. So there are different kind of technique. There is no like silver bullet.
The logging that you mentioned, are there additional tools that you would use to write logs or to analyze logs from concurrent systems? Or is this just good old-fashioned dumping in a text file and reading it later?
So it really depends the system that you're running. There are tools that help you to create these the thread dumps, so you can analyze the thread after they run to see the memory, the thread stacks, the memory slot, and so forth. Personally, when I analyze a performance application, before even use like a concurrent tool, like as I said, the concurrency visualizer, I rather spend a little bit of extra time in memory profilers, right? Because that's actually, they're sort of like related, the two things. And one thing that we're facing these days with managed code is that some extra overhead are introduced when there are too many garbage collection generation in a program, right? So a good memory profiler is able to help you to detect where there are too much memory allocation, and that especially in a multi-thread application, this is also, I can imagine, emphasized because now we have multiple thread allocating, and then you run in different kind of problem. That's when the memory profiler can help you to narrow down where are the bottleneck or where are the situation where there are too much allocation, and optimize that kind of part of the code.
Suppose you would create a tool to help debug concurrent programs. You have unlimited time and money. You can hire whoever you want. What type of tool would you build to improve debugging concurrent systems?
I would like probably that's hard. I have two tools in mind, but one, if I use mainstream languages that share a state that you're forced to use use logs, I use like a deadlock detector. That's actually pretty much very hard to implement, but I didn't have time to try it. But I think it's very hard to implement. However, easier thing to do, I think, is that again, when we're leveraging features such as immutability, right, and or other property that referential transparency, and I'm going to explain what is the property. I like to believe in the future that thanks to this property, compiler should be able to detect and say, okay, I'm safe. I know that the code is immutable. It doesn't produce side effect, so I can optimize the code for you, and don't worry about everything. And something similar that actually Clojure programming language is doing, right? Because again, it's leveraging this property that it said, okay, this code is deterministic, so I could just parallelize it for you without you to be worried. But again, the code had to be written using leveraging this property, and that's where I'm a believer in functional programming in this kind of a situation, because functional programming, it was not really designed to be the silver bullet for parallelism, but really embrace tenets such as immutability as a first construct, referential transparency, and the void of mutation state. So really become clear that functional programming really already use this the ingredient to write correct concurrent program without to be worried about all the thread hazard that are consequently to imperative language that use shadow state.
So you answered one of my questions already secretly in this answer, because one of my questions was, how do concurrency and programming paradigms connect? And you already said functional programming is really good for concurrent programming because of the immutability we already talked about. And you also mentioned referential transparency as a benefit of functional programming languages. Could you explain what that is and why it's a benefit?
Yeah, sure. So functional programming is a bit of the evaluation of the expression. So, and the idea that these expressions are without side effect, okay? Think about side effect as anything can happen outside from the function. Whenever there's a change of state, an exception, or any sort of I/O operation. So something you don't really control. For example, I/O operation that you read from a file system, well, can produce side effect because maybe the file is not in a file system and can throw an exception, right? So any sort of function where the output really depend by the input, which means that every time you pass the same input to the function, the output won't change, it will be the same. And they actually turn out to have a very important property. First of all, because this function depend by only the input, well, you can cache the function because the output will never change. And because, again, there is no side effect, the order of execution of this function, it doesn't matter. So it can really be easily parallelized. So functional programming, it doesn't really make your code to run faster, but really able to structure your program and write your code to be ready to be parallelized without any sort of code changes, right?
Yeah, so what you're saying is functional programming doesn't have side effects, and therefore you could take set functions and run them concurrent because they will not interfere with each other anyway because there are no side effects, right?
That's correct. In the beginning, I asked for to me, concurrent application is a way that you structure a program that can be or be not really parallelized, but really the idea to breaking apart your code in independent tasks. And very similar to functional programming, where the idea composition, which is it's not in a tenet, but it is a very good property about functional programming. When you're breaking apart, big problems is more and smaller function that are easy to be solved directly, and then you glue them together with composition, which is very much similar to concurrency, when you run multiple tasks independently and then be able to compose this task to solve a more complex problem in parallel.
So do you think it is the job of programming language designers to solve concurrency, and that we will soon be in a situation where concurrent problems aren't hard anymore for programmers because the language designers have fixed concurrency and we can just express everything in a regular programming language without thinking about concurrency?
That's my hope, right? Because as I said, I think that compilers should be able to leverage this kind of property that make the program, run concurrently in a deterministic manner. As I said, there are, all the new modern programming languages that I see out there, they're already embracing this tenet, right? And who came late in a run, like, mainstream language like Java and C#, they're introducing this concept in a language, right? So yeah, I think that I don't think it's going to be a long time, but it's going to be part of the compiler able to optimize the code and make it parallel for you based on the property of your program.
But doesn't that take away the freedom of the developer? I want to decide what thread my one process runs on. You're stealing my fun.
Well, I think that there will be, like, for the most, like the 80% of the cases are going to be covered by the compiler. But I still hope that, as you said, that there will be still some control left to the programmer to be able to control what you do it. As I said, like Scala, F#, this kind of modern functional programming languages, I would say that functional first programming languages allowed you still to use mutable state, but you have to be explicit, right? So they still give you a little bit of control, right? There are some cases where mutability is still, a good approach to write performance code to avoid, extra overhead and so forth. I think that they give you first, as default, a great tool to write concurrent code, and then allow you anyways to be explicit and cheat, or maybe do some fancy other technique to leverage mutability and other sort of programming model. But yeah, I think they're going to be like both.
So suppose we have to solve a concurrent problem in a non-functional language, an O language or an imperative programming language, just because it happens to be the language that we use. What are some of the patterns from functional programming that we could still use in C or C++ to solve concurrent issues?
Yeah. So, well, one problem that I see is that we should be able to leverage immutability. But the problem with the leverage immutability in these programming languages is that there is not really compiler that warn you, hey, you didn't write the code immutable, so there is a problem. So it's still left to the diligence of the developer to be sure the code is thread safe, immutable. But you can imagine this is not always the case, unfortunately. But there are some new techniques that are coming in these languages that you actually tell the compiler that this structure had to be immutable, check for me, at least give a warning. But other technique is writing code, embracing referential transparency. So really separate the pure part of your program with the impure part. At this point, because you separate the two kind of behavior, two function, you can just focus on the pure part of the application that are actually when you run your test and they're easy to parallelize and so forth. And the immutable side of the impure side of the application, it can be left, to a different kind of technique optimization that probably, like for instance, impure function. I won't even focus on testing this kind of function because most likely, if you write to the file system or read from a database, well, to me, it's not much sense to test this kind of application. It also became very hard to parallelize due to the side effect. So when you separate the two kind of pure part with impure part, you ease the introduction of concurrent in your application, because you can focus just on the pure aspect of your program.
And then what you're saying is, in any language, you could write pure functions or mainly pure functions, and it will still be beneficial for concurrent programming, even if you're not programming in a pure FP language.
That's correct. It just is a program paradigm, but pretty much you can embrace reference transparency, immutability in almost all languages that were not designed with this kind of paradigm in mind.
And of course, functional programming is amazing. People know I love functional programming, but a criticism we often hear is that functional programming doesn't really scale. But what if you want to build a large system? Immutability is so hard in the real world. What will you say to those people?
Well, I say that, again, this is really like a change of mindset. However, there are some cases that immutability or imperative programming still makes sense. And I don't think that the solution is both extreme, right? I think that functional programming and imperative programming should really coexist in your program rather than stay in opposition. So I think it makes sense, in functional programming, like when there are very sophisticated or low-level algorithms that require performance, but imperative where mutation makes sense, like UI application, front-end application. I would say there is nothing wrong with that, right?
And what are some typical problems we run into if you build large concurrent systems, apart from whether or not we use functional programming paradigm or functional programming ideas? What are typical problems we run into with large concurrent systems?
Well, one of the challenges is really how detect and partition the work that can be run in parallel, right? So it really bring down to the level of granularity or of the parallelism, right? So, for instance, a fine-grained parallelism really facilitate the work to be balanced between different threads, and in this case, the program is partition broken different kind of many small tasks. However, the challenge here is that if you have too many tasks, as mentioned earlier, you can run a situation where you have way too many tasks running parallel. But on the other side, if you try to have more a coarse grain parallelism, so you split the task in a bigger size, like they're larger, then the amount of computation can take place in processor, but also you run in situation where you have very few tasks, so you don't really leverage all the resources. So there are different kind of challenges, and there are not really silver bullet, but measure, and measure. Have a run your application as it is, have a baseline so you can determine the goal and how to improve your program, and then make the changes and remeasure and see actually if your change will improve the performance. So really to decide which side of the granular level of optimization you should change your code, but always measure.
It is always a good idea, I think, to measure, even in a non-concurrent, single-threaded program.
Yeah.
One thing I learned from your book that I thought was really insightful is the idea of concurrent design patterns. Could you explain to the audience what a concurrent design pattern is, and maybe name one or two examples of concurrent design patterns?
Sure. Well, patterns are always great because it creates, a dictionary, a language, between developers, so they know what they're talking about. And there are different kind of design pattern and also concurrent design pattern that really branch in their group in family. Like divide and concur is one very common use when, again, you break a problem in smaller parts that can be solved like in a recursive manner, like when you work a tree structure in parallel, right? That could be something that can be solved recursively and in a concurrent manner. And then other pattern, like the fork join pattern, is very commonly used. That I think that there use sometime even that developer don't know is using it. Like for instance, there are like the parallel for each loop, the same approach that spawn multiple tasks, partition the computation, and then join the result and aggregate the result, right? And in a higher scale, a high level scale, fork join pattern can be considered like part of the MapReduce pattern when you MapReduce your data, and really each step of the computation you can use like a fork join pattern. You spawn multiple tasks and you rejoin, you spawn and rejoin, in each step of your MapReduce, which is called MapReduce, but it's not just MapReduce. Right? It can be different kind of step of your computation. So definitely is a concurrent pattern something that can solve your problem. So there are some cases that some pattern make more sense than other, right? And that's bring the idea, as I said, that if you run like in data parallelism, when you're like a single instruction to be performed against multiple data, probably fork join is a great pattern. Or the problem that was mentioned earlier with the rule engine, when you can use a pipeline pattern where each step of the pipeline, it can be considered like a smaller subset of producer consumer, but allowed you to load balance the work among each step of the pipeline in a concurrent manner.
So are these concurrent design patterns concurrent versions of, let's say, normal design patterns, existing design patterns, or are they entirely new design patterns that have no relationship to existing ones?
That's a good question. This is a bit of both. Like there are some patterns that are, traditional pattern that can be that concurrent can be introduced, and other actually that are just part of the concurrent pattern. Right. For instance, divide and concur, as I mentioned, is a pattern that can be used, for instance, to use to solve the quick sort algorithm. Right. A quick sort can be either sequential or concurrent. Right. On the other side, there are patterns like scatter and gather, where you scatter a lot of information that run in parallel in different kind of system, and then when leveraging some sort of computation that run in different machine, the network, and so forth, and then when they complete, they send you back the result that you can aggregate.
So it's a bit of both. Some of them are concurrent versions, and other ones are entirely unrelated.
That's correct.
One more thing that I want to talk about is asynchronous programming or reactive programming. We already touched upon async a little bit when we were talking about the architecture of Node, which is single-threaded by design. Can you explain what asynchronous programming is and how it relates to concurrent programming?
Yes, actually, asynchronous programming have a very cool property. But think about synchronous programming as a computation that will complete later in the future. You don't know when, but you know going to be completed. There are some cases that it can be notified. So when you start the computation start and be computed in a different thread, and the main thread is going to be notified when the computation is completed through maybe like a callback that is quite is quite popular. Or but there are other cases, like for instance, it can be like fire and forget. So you just send an operation and you don't care about the result. But what is cool about the asynchronous programming is that based on I/O bound operation, which involve just a little bit of CPU computation. So really leave the CPU light to do other operation, because the idea is that the asynchronous operation is going to be computed somewhere else. For instance, a web request, right? You send a web request, they're going to be computed probably on different servers, which is pretty cool, because now we can leverage a property that I like to call unbounded parallelism. And I say unbounded parallelism because when I talk about parallelism, it's like concurrency, but with hardware constraint. So parallelism can run only in a multi-core machine. However, asynchronous programming, due to the fact that the computation runs somewhere else, well, you can achieve true parallelism even a single core machine, right? Because you can spawn thousands of asynchronous operations on a single core machine that will be computed in a different place, and then just receive the notification when they complete and continue the work. So I think that's a very cool property about asynchronous programming, and which step further is really is the base programming model to implement scalable system, which means is a system that is able to cope to many requests at the same time, because again it's not really bound to the CPU resources you have, but just to IO resources. So this is very cool. The other thing that you say about reactive programming, it kind of connected to asynchronous programming, because it allowed you to treat stream of a synchronous event, right? But like in a way that you do operation with a collection, right? So really bring up the composable aspect of this operation, so you can iterate it through this stream of a synchronous event, which pretty much are data, like an array, like word, like an array or a list and so forth. So really, reactive programming free you from handling complex callback from asynchronous programming, and make your code more readable, less prone to bugs, and easy to understand.
But reactive programming modules or libraries exist in many mainstream programming languages nowadays, also non-functional programming languages like JavaScript, for example. How does this fit into your story of functional programming is best for concurrent programming?
Well, so I think that reactive programming is just a pattern that can be replaced any sort of the observable pattern. But what is great about reactive programming is that I like to think of programming as can be used like at both the head and the tail of your concurrent program. One part can be the part of your program that send data to your algorithm that can run concurrently, but also the other side of the algorithm at the end, you can feed reactive programming, with this event, and just manipulate the event to ultimately, aggregate the result, do something with your result, right? Aggregate the result, filter the result, and so forth. There are actually a very cool library that is based on an agent programming model, which is a message passing programming model. But the idea is that whenever the agent receives a message, compute a message, and then send out the result, and then you can plug reactive programming to receive this message and do something in a more composable or functional manner, right?
So you just mentioned message passing as another pattern. Maybe not everyone is familiar with this model. Could you explain what is a message passing approach?
So message passing is based on an old idea where instead to share a state the part of your program communicate each other only through messages. And this brings in the idea of a actor or agent. There are subtle different there, but these are very small union computation that communicate only through messages, which means that they are isolated, because now this unit computation, the trick is just single-threaded, right? So if this unit computation is single-threaded, you just remove all the complexity due to concurrency. So the parallelism is achieved by having many actor or agent that communicate each other through message passing, which again, the message, you get best of both worlds. The message is immutable, okay, so cannot change, but also the agent are protected, because being single-threaded, you can even have a state on the agent that is thread safe intrinsically, because only the agent can access this state. As I mentioned, because the thread is a single-threaded, you won't run in sort of race condition. So it's a great programming model, because you can structure your code really in a small unit that you can pass the messages like sort of like great for the pipeline approach we mentioned earlier. So each agent can send a message to the next step of the pipeline, which is an agent. And parallelism is achieved in this case by having multiple agents run for each step of the pipelining. But this is transparent by the developer, so you just send a message to the next step. And when you send a message, the agent actually is able to load balance the work among other agents that are part of the step of the pipelining.
So how agent-based programming relates to concurrent programming is that you can have a system in which agents just send each other messages which are immutable, and every agent would have its own thread, so that's thread safe by default. Do I summarize that correctly?
That's correct, yes.
Okay, so lots to choose from in concurrent programming. We can have programming languages that solve the issue, or immutable data structure, or agents. Is there anything you want to add as possibilities that people should consider if they have a concurrent situation at hand?
Sure. So when you write your program, I think immutability is a great tool, but it's hard to achieve. A better solution, or easy solution, would say no better, but is like the share nothing approach, like the message passing we just talked, right? And we see these days that this has become also like an architecture kind of approach. Like we have microservices that pretty much don't share state between other microservices. We have the idea of the CQRS pattern, command query responsibility segregation, where actually this pattern, the idea is that separate the part of when you read only part of your application to the part of the application that actually write and create side effect. And when you actually split this kind of part of your program, because you share nothing, that's actually become easier, not just to reason about your program, but easy to introduce parallelism, because now it's easy to have tasks that run in parallel for the specific part of code that don't produce side effect because they don't share state. Or you can decide, well, instead to task, I want to use agents, right? So at that point, you can introduce agent easily, because you don't have to worry about the part of your program that creates side effect, because already are separated in a read-only manner, so they can be easily spawn multiple agents without run in unwanted behavior, and your code still run deterministically. So that's definitely a good approach there to start.
Thanks. I'm all out of questions. I think I've asked everything I wanted to know. Is there anything more you want to add to the show?
Well, first of all, I want to thank you to having me here. I think we cover a lot of material, yes. And I think that we can post something in the website with some added resources that can prepare for the listener.
Yeah, absolutely. So we will definitely link to your book, of course. Is there any other place on the web where people can read more about you and your work?
Well, there are great video. I think that personally, I really love message passing concurrent programming model. So, and that's it's a great, paradigm to start with to write, concurrent program. I will start in that way and start to look around this kind. There are many resources out there. It's very hard to tell which one the best, which one not. But definitely, that's what I would like to motivate the listener to start investigate the message passing programming model.
Okay, thanks. Thanks a lot for being on the show, Ricky.
Thank you for having me.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.